So we want to talk about roots, limits, and end behavior now. First, let's start with roots. Now you know roots from Algebra 2 and Algebra 1 are wherever a graph crosses the x-axis, and we're used to calculating those roots by setting a function equal to 0 and solving for the x that makes that so. But we're about to start a journey in which graphs are much more complicated. Sometimes they're going to have shapes like this, and sometimes they'll be more trig function-y, which we saw last year as well. And we don't have really the luxury of calculating roots in the same way that we did before. So we're going to do, instead, we're going to take advantage of another fact that you may or may not have noticed about graphs before. And that is, if you have a graph that looks like this, let's just go with that because it's nice and wonky. So if you have a graph that looks like this, one of the things that you may notice is that for this first set of the graph, this part here coming up from negative infinity, all of the y values or the output values are negative. And then once I cross over the x-axis, as long as I stay above the x-axis, all of these values are positive. Then, just to continue the theme, I come down below the x-axis again, and the act of crossing over from the positive y side to the negative y side means that our function values are going to be negative. And then again, cross over, and everything up until I cross back over the x-axis will be positive again. So what we want to do is start to look at determining where roots exist by looking at the change in sign of the output of the function. So let's do an example. I want to know where are the roots when the function of x is x cubed minus 4x plus 2. And we're actually asked to find on the interval where a root might be between my negative 4 and 4 inclusive. All right, so I've already loaded this up on my calculator. You can see that the function we're talking about is exactly the same function I've written here. And let's look first at the graph so we kind of get an idea of what it looks like. Great. So I know there are 3 roots on this graph between, and I happen to know this already, you would have to figure it out, but negative 4 is outside of all 3 of the roots, and positive 4 is as well. So all 3 roots are included on that boundary. So what we're going to do is we're going to use the table. So let me set up a table. And then use the calculator. You can see that I've already set up my table to start at negative 4, the beginning of my interval, and I'm going to step forward 1/10 of a unit for each input value. So if I look at my table, I have a negative value. So what I want to do is just scroll down on the interval until I have a positive. So here we are. My y outputs have gone from negative to positive right here between negative 2.3 and 2.2. So let's go ahead and write those in. So negative 2.3 and negative 2.2. At negative 2.3, I'm looking at negative 9.6. I'm going to round up, negative 0.97. And at negative 2.2, I'm also going to round up or round down to 0.15, to positive 0.15. So the information I can take from this is that somewhere between negative 3 and negative 2, somewhere between negative 3 and negative 2, there is a root. And it's not a pretty root, it's a fraction. So there's no way I'm going to be able to factor to find that root. I'm going to have to use other evidence or other information. So let's go ahead and do exactly the same thing to find the others. So I'm going to scroll down. Now I'm looking for the sign of the output values to change to a negative. paid better attention to the graph, I'd know exactly what I was looking for, but no. All right, here we go. So I have a positive at 0.5, positive 0.5 input, and the output there is 0.125 or 0.13, and then I have a negative output at 0.6 input. And my value is negative 0.18. And the takeaway again from this information is that I don't have a root at an integer, but I definitely have a root somewhere between 0 and 1. And our last root, our last time our graph crosses over, and I know I'm looking for 3 because I already saw the graph. So the last time is between 1.6 and 1.7, and the outputs in those cases negative 0.30 and positive 0.113 or 0.11. So again, now I can say that my third crossover or my third root is between 1 and 2. And if I look at my graph, fingers crossed, I can see that that's exactly what I would expect. Somewhere between, I have the trace function on, so I can see right here I'm approaching x is 1.89, and as I've crossed over right here at the 1, and that's exactly what I expect, somewhere between 1 and 2. Keep tracing, somewhere between 0 and 1, and we can see the decimal input and the decimal output. And then on over here, I should expect a value greater than 2 but less than 3, and I did, and I have that. So at this point, when we don't have pretty functions with pretty factors, the best we can do is approximate the location of where a root exists on the graph. And using a table, we can see that we have approximated definitely within one integer value where this graph has roots. So now let's look at limits and end behavior. So we looked at limits before, but this time we want to look at what happens to a graph, or how do we describe the end behavior using limit notation of a graph that does something like this, kind of like the graph we had before. So we want to be able to explain this behavior using our new language of limits. So we can see from Algebra 2, we would say that the end behavior is to move toward positive infinity on the right and toward negative infinity on the left. But in PreCalc and Calc, we need a different kind of language, something much more specific. And so the language we use is I'm going to say that the limit, as our x values approach infinity, right? So my x values, my input values are getting closer and closer to infinity. The limit of this function is positive infinity. My y values are getting closer and closer to infinity. And on the other side, the limit, as my x values approach negative infinity, so I'm choosing x values closer and closer to negative infinity, then my y values are approaching negative infinity. That sound you hear is Jason getting his new whiteboards. And just like we did before, we can use our graph. So I've put a function on my graph, and we're just going to have to listen to Jason get his whiteboards. I waited long enough. I took a pause and waited. So we're looking at y equals negative x to the fourth plus 8x cubed plus 3x squared plus 6x, yikes, minus 80. So using algebra 2, the only thing we can possibly do with this is we know that there's a y-intercept at -80. Everything else we can't do. We don't really know how to factor this to find the roots. We don't have a lot of resources, but we can look at the table and get an idea. Now, I'm not going to write the table out, but I'm going to talk about it here. So I started at 0, and if I go, and I've set my increments to 100 because I know what's going to happen, so I've already set it up that way. So if I look at the table, every time I move forward on the x-axis by 100, I move far away. Look, I'm already at negative 9.2 times 10 to the 7th. I'm already at a big number. The next one, 1.5 times 10 to the 9th. I am definitely zooming off toward negative infinity. So what this graph actually looks like, and it doesn't even fit on my table, on my screen, on my calculator very well, so I'm just going to show you, is it comes up this way, it crosses at -80 as we expected. If I wanted to find this root, I could evaluate by positives and negatives. It peaks up here and comes down again. And so we can see that happening. The output values are getting closer and closer to infinity. So I'm going to negative infinity. So I'm going to write the limit as x values approach positive infinity of this function equals negative infinity. And the same thing if I go in the other direction, you see exactly the same thing happening. I'm going again to negative infinity, and I'm going there fast. So the limit on the left-hand side as x values approach negative infinity, meaning my input values get farther and farther out toward infinity of this function, the limit equals negative infinity.